Let me remind you some things that we have observed about Z. One thing that we know is that it is embedded into the field of rational numbers. And the field of rational numbers is written as the set A over B, where A is an integer and B is a non-zero integer. And we say that two fractions are equal if we can cancel out certain factors in the numerator and denominator and get the same pair. So it is a set of these fractions after some equivalence relation. Another thing that we know about integer numbers, and you could have used it in solving your second P set, is that if we have an integer, we can get its prime decomposition of the form A is equal to P1 through Pk to the power n1 through nk, where every Pi is a prime number. We saw that every ideal of Z is principal, that is of the form brackets A for some element A in Z. So we have an ideal generated by one element. And Z has a norm which is not defined yet, but to which I have referred as absolute value. Absolute value. And we have a Euclidean algorithm with respect to this norm. So we can divide with the residue, and the residue is smaller in the sense of this absolute value than what we divide by. And in the next several lectures, we will be working towards abstracting these notions, like trying to push it further and generalize it further to other rings. Today we will define fields of fractions for integral domains. Next time we will talk about factoring, about prime and irreducible elements. Prime and irreducible elements and factoring. This notion, this property, is called being a principal ideal domain. So when every ideal is principal in a domain. This is called a principal ideal domain. Or it is very commonly denoted as by PID. And Euclidean algorithm is the defining property of Euclidean domains. So let's start with the fields of fractions. Fix an integral domain R. And define its field of fractions as follows. It is denoted by frac R, and as a set, it is defined as pairs A over R, where A is an element of R and R is a non-zero element of the ring. And as with the case of integers and rational numbers, we want to introduce an equivalence relation on these symbols. We say that A over R is equivalent to B over S if and only if AS is equal to BR. And let us prove a theorem about this construction. R a domain, and F denotes this field of fractions. Then first, F is a ring under the natural operations, under A over R plus B over S is equal to AS plus BR divided by RS, and A over R times B over S is defined as the product AB divided by the product RS. The second property is that F is a field which justifies its name. And finally, R can be viewed as a natural subring of its field of fractions. We are sending an element R to R over 1. For the proof, the zeroth part, which should always come in the first place, is that this tilde, this relation does define an equivalence relation. So tilde is an equivalence relation. So it is easy to see that it is reflexive and symmetric. So first, it is reflexive because for A over R, A times R is equal to A times R. And it is symmetric because we can just change this, well, we can move AS to the right and BR to the left. It is less trivial to check that it is transitive. So let us assume that we have A over R, which is equivalent to B over S, and B over S is equivalent to C over T. It is the same as saying that AS is equal to BR, and CS is equal to BT. Now, consider the element AST, the product AST. It is equal to BRT via this equality. And further, here the second equality, we change BT to CS, so we get CSR. And now let's take AST and CSR and consider it and move CSR to the left. So this equality is the same as saying that AST minus CSR is equal to 0. But now by distributivity, we can write it as S times AT minus CR. This is equal to 0, and S, being in the denominator, is not equal to 0. And recall that we assume that R is a domain. This is very important because it means that S is not a zero divisor. So if this is equal to 0 and S is not a zero divisor, then AT minus CR is equal to 0. So we conclude that AT is equal to CR, which means that these two fractions are equivalent. Now we are ready to start proving the first part, that F is a ring. So again, you would have to prove that addition and multiplication are well defined, that they do not depend, the result of these operations does not depend on a choice of a representative from the equivalence class. Representative. But I would like to omit this part. And I will skip directly to showing that the ring axioms are satisfied. For addition, it is clear that it is commutative because AS and BR, we just change, move them from left to right and vice versa. And it has the 0 element. 0 fraction 0 divided by 1. Or basically 0 divided by a for any non-zero a. And now let me quickly show associativity. So a divided by r plus p divided by s plus c divided by t. This is equal to, if I do this part first, I get the following expression. As plus br divided by rs plus c over t. And we can write this as ast plus brt plus crs divided by rst. And on the other hand, if we take bs plus ct first, we get a divided by r plus bt plus cs divided by st. And then we follow the rule again, and we see that this is in fact equal to this fraction. So we have ast plus brt plus crs here divided by rst. It is even easier to show that multiplication, as defined here, is commutative and associative. Commutative, associative, and possesses the multiplicative identity, which we write in the form 1 over 1, or also a over a for any non-zero a. And we can show distributivity again by doing a simple calculation. A over r times b over s plus c over t. First, let's calculate the sum here. It is equal to a divided by r times bt plus cs over st, which is equal to a bt plus a cs divided by rst. And now let's see what is the other side of distributivity. A divided by r times b divided by s plus a divided by r times c divided by t. So we want to see whether these two are equal. So in order to multiply them, we write, just basically make this dot into a longer line. We have AB divided by RS plus AC divided by RT. And this is equal to, by the rule of addition, to AB RT plus AC RS divided by RS RT. And now, in order to show that these two elements lie in the same equivalence class, we need to multiply this enumerator by this denominator and this denominator by this enumerator. But note that in this enumerator and denominator we have an extra set of r's. So you can see that this crisscross product that by doing this crisscross products we would get equal quantities because we have ABT plus ACS times R, and so we get an extra R for the yellow star, and here we get an extra R for the pink star too. For showing that F is a field, take any non-zero element A over R in F, then R over A will be its inverse, because R over A times A over R is RA divided by AR, and we can see that it is equal to the multiplicative identity because RA is equal to AR. Let us see why R is a subring of its field of fractions. So we need to check that the map iota that sends R to R over 1 is a ring homomorphism. So let's consider R plus S. It goes to R plus S over 1, which we can see is equal to R over 1 plus S over 1. So, and this is iota of R, and this is iota of S. So this map is additive. Further, if we have a product of R and S, it goes to the product of RS divided by 1, which is equal to R over 1 times S over 1. And we see that iota of RS, this side, is equal to iota of R multiplied by iota of S. So iota is a homomorphism. And let's consider the kernel of iota. Let's take some element R in the kernel. It means that R over 1 is equal to the fraction 0 over 1. And this is, by the equivalence relation, equal to R times 1, equivalent to R times 1 being equal to 0 times 1. But 0 times 1 is 0 and R times 1 is R. So we get that R is equal to 0. So the kernel of iota is 0. And thus, this map is an injection. This construction looks pretty formal, but note that we did use that R was an integral domain several times in the proof. Otherwise, if we try to repeat this construction for an arbitrary ring with 0 divisors, let's say that A times B is equal to 0, and these are 0 divisors in some R, which is not an integral domain, then we would not be able to multiply 1 over A by 1 over B, because then we would get 1 over AB, which is 1 over 0. And if you see 1 divided by 0, you should naturally get very, very suspicious. So the upshot is that fractions work best for integral domains. As usual, we introduce some definition or construction, and we consider some examples afterwards. So example/definition. If K was a field, then we already defined what its ring of polynomials is. Oops. And further, we define its field of fractions, denoted by K parenthesis X. We introduce the field of fractions of the polynomials, and this field is called the field of rational functions. So its elements are all the formal rational functions in X of the form some polynomial of X in the enumerator and some non-zero polynomial in the denominator. Another example / proposition is that if K is a field, then it is its own field of fractions. Then frac K is equal to K via this embedding from K into the field of fractions. And let's see this. So we have this iota from K into the field of fractions. Then we already saw that that iota is injective, so I want to prove that iota is surjective. So let's take A over B in frac K, then A over B can be written as A times B inverse over 1, because A times 1 is equal to B AB inverse, And we know that every non-zero element in a field is invertible. So A over B lies in the image of iota. Let me show you how I like to think about fields of fractions. So let R be our integral domain, and let F be its field of fractions, frac R. And if R is a non-zero element of R, then I can introduce adjoin a formal inverse. R square brackets alpha mod out by the ideal, where I say that alpha is the inverse of R. And I denote this construction by R square brackets adjoin 1 over R. You can check that this ring can be embedded into the field of fractions. Then I want to invert some other element in R, and so I consider this R adjoin inverse of R, and I adjoin 1 over S2. And I can notice that, in fact, inverting R and S is the same as inverting 1 over Rs. And this also is a subring of the field F. And I imagine the field of fractions as the limiting ring that we get from R by adjoining all the inverses. And via these embeddings, so for every element R, for every non-zero element R in R, we can consider this as a subset of F. And as a set, F is equal to the union of these subrings. And this is because for every A over R in F, A over R can be viewed as an element of R adjoin 1 over R for a certain R. So F consists of R plus all the inverses of all non-zero elements.